Okay, so I just wanted to make a short video going over acid-base review number 1. Hopefully you didn't find it that difficult. Getting the conjugates, obviously, the acid is the donor, base is the acceptor of the proton, so hopefully all of that was pretty simple there. The amphoteric deal is you being able to tell that it can be both an acid and a base. And so when you're looking at these, if it has a hydrogen, it can act as an acid. So the one that can't act as an acid is the SO4 2-. It can be protonated, which shows it has one in the conjugate acid category. So it can accept a proton, it can act as a base, but it can't act as an acid because it doesn't actually have a proton to act as an acid. So that's why the last one's the only one that can't be amphoteric. On the next section here, getting the pH of a strong acid solution, you just take the negative log of the strong acid concentration. For the hydrofluoric acid, though, that is a weak acid, so you see they made an ice table there. It looks a little different because they included a column for water, even though I usually just leave those out. Anyway, it worked that out. They used the X is small approximation, if you notice. They just said that the 0.150 minus X is equal to 0.150, and then they got the hydronium concentration, took the negative log, and got 1.98. Now, the next part, the percent dissociation, remember, that is the concentration at equilibrium of hydronium divided by the initial acid concentration. And so since the X value is 0.0104, that means that they subtract that from 0.150, and what it looks like, sorry, I was talking about the wrong thing. I was looking at the hydrofluoric acid. So X is the hydronium concentration. Divide that by 0.150 times 100, and you get 6.9%. On this one, they wrote it based on the relative concentration, so the bigger ones are more concentrated. So when it says which one's the stronger acid, well, since the products are not favored, they're smaller, that means there's less of them, therefore there's more reactants, which means the reverse reaction is actually going to be favored. So that means the hydronium is going to be the stronger acid because there's less of it. It means it's going in the left direction. On the next one, you got hydrosulfuric acid, hydrocyanic acid. Rewrite the equation above to show which one would be more concentrated in solution. You're doing the same thing as they did up top, except for this other equation. If you'll notice that hydrocyanic acid is the weaker of the two by 3 powers of 10, and so that's why it is larger. Let's see. When you're solving for this, you just use the circle of life. It should still be up on my board. You just take the negative log of the hydronium to find the pH, the negative log of the hydroxide to find the pOH. pH plus pOH equals 14. Hydronium times hydroxide is 1 times 10 to the negative 14th. Obviously, if the pH is less than 7, it's acidic. If it's greater than 7, it's basic. So that's how they did all of that. Here we have a weak acid solution. It's a generic dissociation equation. Calculate the hydronium concentration for a 0.3 molar solution of the weak acid. Well, in this case, they gave you the pH, which means they gave you the concentration of hydronium at equilibrium if you do 10 raised to the negative pH. So that means you got 5.6 times 10 to the negative 5th for the hydronium concentration. And so then on C, when they're filling in the ice table, they started with 0.0300, and then at equilibrium, your X value is 5.6 times 10 to the negative 5th, and then they just filled in all of those values up here, and then solved for the Ka value, which was 1.1 times 10 to the negative 7th. they did 2 sig figs because the pH has 2 sig figs there. So down here, you're just plugging in the strengths based upon the Ka and Kb. Obviously, the larger the Ka, the stronger the acid. The lower the Ka, stronger its conjugate base. So hopefully you're able to figure that out okay. Diprotic acids, remember if you have, well, basically every single time you have a diprotic acid, it's like a mixture of weak acids, but the K values are going to be so far apart you only have to worry about the first one. So they did the 2 equations for each hydrogen up top, but then when they did the pH, they only worried about the first one. So that's why you only have one ice table there, because they only worried about the first hydrogen. Now, for the second part, to get the SO3 2- concentration, you got to go ahead and do the second ice table, which is annoying, but that's what they did. And so they ended up doing both ice tables anyway. But hopefully that all makes sense. If not, remember, you can ask me and I will try to help you along. State whether it's acidic, base, or neutral. So you're looking at both the cation and the anion. If the cation is acidic and the anion is neutral, then it's acidic. If the cation is neutral and the anion is basic, then it's basic. If they're both, then you got to compare them. In this case, I don't believe, no, you didn't have any that had both an acid and a base, so that made it pretty easy. We got potassium cyanide. So since potassium's neutral, that means you just have cyanide. That's going to act as a base. So that's why they wrote the equation for cyanide acting as a base here. They just forgot about potassium, because who cares about potassium? And then they used that equation to get the Kb for cyanide. And yes, you could have just looked that up using the tables, but they wanted you to show your work. So what you did was you took the Ka of hydrocyanic acid and you plugged it into the equation where Ka times Kb equals Kw. You could have also worked it through the pKa's, but that would have been an extra step anyway. So then they have you calculating the pH of a 0.02 molar solution. So just use your equation above, work out the ice table for cyanide acting as a base. Then once you get the X value, that's actually going to be your hydroxide concentration. So when you take the negative log, that's the POH there, and then they did 14 minus the POH to get the pH. Let's see. For ammonia, that's going to be a base. And so you wrote the equation, do an ice table again, calculate the K for the conjugate acid, so you do the K times Kb equals Kw again, and then write the equation for the ammonium, since chloride is neutral. Hopefully all that makes pretty good sense. It's just kind of more of the same. Then you have to rank them. This is like your last homework, so hopefully that kind of all makes sense. If not, let me know. I'll kind of explain it. The top one has to do with electronegativity. The middle one also has to do with electronegativity, because they all have the same number of oxygens. And so since chlorine is the more electronegative, that's why it goes to the strongest. On the last one, you have more oxygens, and you have the more electronegative central atom. So it's kind of a combination of electronegativity and oxygens. I think I just had you go through number 11. Common ion, we didn't talk a whole lot about it. We're going to talk more about it later, but essentially what we're saying is if you have hydrofluoric acid and then you put potassium fluoride in with it, that's going to cause you to have an initial fluoride concentration. So when you make your ice table, and I just realized he didn't do the key part here. So HF in water is just going to be HF plus H2O is going to give you your H3O and F minus. So when you make your ice table, you have HF, H3O, and F minus. So it'll look like this. Okay. And so, sorry for my handwriting. You have 0.2 moles. It's in a 1 liter solution, so that is the molarity. 0.2 here, 0 here. And then, since we have a potassium fluoride solution, we're going to go ahead and start with 0.1 here. So then we'll do, this is just like a mixture of a weak acid and a strong acid solution. So this will be plus X and plus X. So you got 0.2 minus X, X, and 0.1 plus X, like that. Then you can use the Ka, 7.2 times 10 to the -4th. That is going to allow you to use the extra-small approximation. So you got 0.1 plus X times X over 0.2 minus X. This can go to 0. This can go to 0. The 0.1 over 0.2 is just the same thing as 1/2, right? So you can work that out from there, solve for X. I think that should be pretty easy. Then your X value obviously is going to be your hydronium concentration. Sorry, well actually I do have a calculator here. Let me just work this out real fast. I'll let you do C. If you can do B, I'm not that worried about C. So let's see here. So I got an X value equal to 1.44 times 10 to the -3rd. And that is my hydronium concentration. So to find the pH, I just take the negative log of that, and I get 2. What do we want? It looks like we want 2 sig figs. 2.8 is the pH. Alright, so that's how you would solve for that. On C, you do the exact same thing, except you're going to start with 0.1 up here instead of 0.2. So obviously, if you have less acid, that means your pH is going to go up a little bit. So whatever you get should be higher than 2.8. Anyway, I'm sorry that turned a little bit longer than I thought, but hopefully it's helpful. Please email me with your questions. Let me know how I can help you. Get ready for the test.